Good evening. My name is Anvesh, and we'll be today discussing the solutions to the course Interfacial Fluid Mechanics. Week 7. Okay, week 6 assignments we'll be discussing. This is the week 7. Um, so essentially, in this week, we have gone over Jurin's height and how capillary rise phenomena occurs, with keeping in mind the dynamics. So the lectures in this week we have gone over the dynamics of capillary rise essentially. Along with it, we have also looked at coating flows and the famous Landau-Levitch coating. So let's go ahead and start. Um, so this is assignment 6 solution. So let's go with the first question. When deriving the scaling laws for Landau-Levitch dip coating, what was the need to rescale the length scales in the transition region? So let's look at the options we have. In the transition region, uh, mu in the transition region, mu del u by del x square del square and mu del square v no del square u by del y square. So first is del mu uxx, which is del square u by del x square, is very much smaller than mu u del square u by del y square. The option 2 is in the transition region, viscous effects become important, which was ignored in the static region. In option C, in the transition region, gravity effects become negligible. So if we look at the diagram, let me get some space here. Insert space. Second. Okay. We have the Landau-Levitch dip coating. And if we look at this figure, uh, this is the transition region, and essentially the red dotted line is the static meniscus. So, from being a static meniscus to the dynamic case of getting wetted, we transition from being in a gravity driven flow to a viscous driven flow. So gravity driven static situation to a viscous driven dynamic situation. So option C is correct. And then in the transition region, as we have just discussed, viscous effects become important. And essentially, if we look at this diagram, 1 second, I'll just. Yes, now we have the coordinates that we use is this is y and this is x. So if we have such a coordinate system, u changing with respect to x square, that is in this direction, is a lot less, and a lot less changing is a lot less essentially in this vertical, in the x direction, than in the y direction. So del square u by del y square. So therefore option A is also correct. So the correct option is option D. All of the above are correct. Let's go to the second question. A plate is emerging from a liquid to air, getting coated at the speed of 200 micrometers per second, the plate speed. You may assume the following parameters for the coated liquid. Viscosity is 1 millipascal, density is 1000 kg per meter cube, surface tension is 0.072 Newton per meter, and gravity is 9.81 meters per second square. We are asked to calculate the approximate thickness. So first we'll write down what is given. So the plate is given as 200 micrometers per second, which is equals to 200 into 10 power minus 6 meters per second. Viscosity mu is equals to 1 into 10 power minus 3 Pascal second. Density rho is equals to 1000 kg per meter cube, and surface tension gamma is equals to 0.072 Newton per meter, and gravity is 9.81 meters square per second. So we are asked to find the coating thickness, H. So we know that the capillary length, first we need to calculate the capillary length. LC is equals to gamma by rho g. So which is equals to 0.072 divided by 1000 into 9.81, which is equals to 0.0027 meter. So once we have the um, capillary length, we need to find out the capillary number. Capillary number Ca is given by mu u by gamma, and here u is plate velocity. So capillary number can be written as mu, which is mu we had 10 power minus 3, u which was 200 into 10 power minus 6, divided by gamma, which was 0.072. So this comes out to be capillary is equals to 2.85 into 10 power minus 6. The coating thickness is given by H infinity. H infinity is equals to, we know this from the notes, is 0.9458 and 458, yes, into LC into capillary power 2 by 3. So we have, this is 0.9458 into 0.0027 into 2.85 into 10 power minus 6 to the power 2 by 3. So H infinity is approximately equal to 0.5 micrometer. Therefore, the correct options is D. H infinity is equals to 5 micro. Oh, sorry, it's not D. The correct option is A. It was 0.5. 0.5. Correct option is A. During the final stages of capillary rise in a tube, the fluid height approaches the Jurin's height with an exponential delay. Which one of the below scaling law correctly describes the relationship between the velocity of the fluid z dot, radius of the tube A, and the kinematic viscosity mu? So given we have z dot, which is the velocity, we have radius of the tube A, and we have radius of the tube, which is A, and we have kinematic viscosity. So we are in the viscous regime of, let's say, we are asked to find the scaling between z dot and a function of radius and kinematic viscosity. So we know we are in the viscous regime. So in the viscous regime, we have the, so first let me get some space. In the viscous regime, we have 2 gamma cos theta by rho A minus 8 mu z z dot by rho a square minus gz equal to 0, where h we know is the Jurin site and it is equals to 2 gamma cos theta by rho g a. Okay. Now, if we rearrange to get z dot, we have uh, we have z dot is equals to 2 gamma cos theta. 2 gamma cos theta by rho a minus gz, and we have 8 mu z by rho a square. So we multiply and divide by g. This is equals to 2 gamma cos theta by rho a g into g minus g z. Wait a second, let me just check. Okay, we'll do step by step. Something is wrong. So we divide the entire equation with g. G, 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 g. So then we have 2 gamma cos theta by rho a g, which is h, minus 8 mu z z dot by rho a square g minus z is equals to 0. So now we have, if we take it to the left hand side, we have, oh sorry, right hand side, we have 8 mu z z dot by rho a square g is equals to h minus z. So now we have z dot is equals to rho a square g by 8 mu z h minus z. Taking z common, now we have z dot is equals to rho a square g by 8 mu into h by z minus 1. Okay, now we need to non-dimensionalize the quantities. So how do we proceed? So let's say that the star be the non-dimensional quantity. Z star is equals to Z by H. Then we have Z dot is equals to rho G A square by 8 mu into Z into 1 by Z star. So we have then we see the scaling of Z dot as rho A square by mu, which is indeed A square by mu. So the correct option is D. Z dot of D is now we have the question. When a capillary tube is dipped into a fluid bath, the fluid rises in the tube to be the Duran's height. When the tube is hydrophilic, see figure 1, consider another tube with identical conditions except whose total height is less than that of Duran's height. What will the fluid what will happen to the fluid as it reaches to the top? So essentially, we are asked what will happen to the case 2. So the options are A, the fluid in the tube will overflow. B, the fluid in the tube will simply settle down at a height lower than the height of the tube. C, the meniscus will reach the top and then slowly drain out. And D, we have the meniscus reaches to the top and gets pinned to the edge without spilling. So we have let's see, we have height h is less than 1 second. Sorry, wait for a second. I have lost my connection. Sorry for the inconvenience. I lost my internet connection. Okay. The height, this is a case where a capillary tube is dipped into a liquid bath, and the height to which the liquid can rise is less than the Duran's height. So when such a case happens, the water in such a case, if we have in such a case, fluid will rise to the top, reach the top, and we may see a small bulge, and then because of the bulge, the fluid gets sucked in again, and then we see a small depression. And after these oscillations damp out, the final case is when the fluid gets pinned to the corners and becomes flat. So this is the final state. So the correct option here would be D. The meniscus reaches the top of the tube and gets pinned to the edge without spilling. So there will be a capillary rise where the surface tension force dominates and makes the fluid to rise up. And as it reaches up, due to inertia, it will slightly overshoot and create a small bulge. And again, due to the pressure jump condition, the pressure inside the capillary tube will increase and will in turn suck in the fluid, therefore creating stage, first stage, second stage, third stage, and then this is the final state. So, firstly, the fluid will rise up, then, due to inertia, it will slightly overshoot and create a bulge, which in turn pulls the liquid back in and creates a depression. And then, as the depression in turn again, the pressure jump is in such a way that the fluid tends to rise up. And once these oscillations damp out, we see that the fluid gets pinned to the sides, and therefore in the final state of the fluid in capillary tube gets pinned to the corners and stays flat. So therefore the correct option is D. So next question is, in the discussion on dynamics of capillary rise in tubes, we obtain the Washburn's law. Washburn's law is, so it's given that Washburn's law is z of t is under root t, goes as under root t, and then therefore the velocity rises as z dot of t goes as 1 by root t, which clearly diverges at t equal to 0. Z of t goes to infinity as t goes to 0. Therefore, z of t diverges. Z of t diverges, and the divergence limits the validity of Washburn's law for very short times. What new physics prevents the occurrence of the divergence in velocity? So, in Washburn's law, we basically ignore or neglect the inertia. But if we look at the tube, we see that the liquid rises up with a high value of velocity z dot of t. So in the initial stages, when the tube is when the level of water is moving up uh, at very short times, the inertia force cannot be neglected as there is significant value of z dot. So, let us look at the options. It says the velocity at short times means that inertia cannot be included, and inclusion of inertia prevents the occurrence of the divergence. So, in Washburn's law, basically we ignore the inertia and therefore we get such a scaling. But if we include the inertia, which is the new physics, the divergence can be prevented. Therefore, the option A itself is correct. We'll read out the other options as well. Gravity force was neglected in the derivation of Washburn's law and needs to be included to prevent the divergence. Okay, this is not the case. Gravity is indeed included. Let me look at. Okay, then option C, surface tension force is negligible at short times but was considered in the derivation of Washburn's law. Removing this force eliminates the divergence. No, this is untrue. And then finally, the high velocity at short time requires inclusion of dynamic pressure, which was ignored in the derivation. Option A is correct. So, option A. Um, Now we have, in the course, we have seen scaling law for Landau-Levitch coating as given. This law was derived with the assumption capillary power is less than 1. Consider a situation where the capillary number is not so small. The dynamic meniscus region assume. In the course, we have seen the scaling, and then it's given that for capillary number less than 1. Consider a situation where capillary number is not so small. The dynamic meniscus in the dynamics meniscus, assuming gravity effects to dominate over surface tension. Repeat the analysis carried out in class. What is the new scaling law one obtains? In the below expressions, bond BO is the bond number. Find scaling of balance between surface tension and scaling of balance between surface tension and gravity. So the scale for viscous forces is um, So first we'll write down for the surface tension force. Oh, okay. What was... Sorry. Okay. I made a mistake. Um, so we need to balance. This was correct. We'll write down the scales for gravity and viscous forces and bring in the surface tension force later on. So first we'll look at force of viscous, which scales as mu u by h square, where h is the height, mu u by h square, and force of gravity rho g. So now if we balance these both forces, we have mu u by h square by, by rho g, and also square by gamma. So we'll divide both sides by LC square by gamma, which is basically meter square by Newton per meter. So which is basically meter cube by Newton. So it is basically 1 by force per unit volume. So it is basically force per unit volume. Then once we divide that, we have mu u by h square LC square by gamma, scales as rho g LC square by gamma. We know the bond number is equals to mu u by gamma. Oh, sorry, this is the capillary number. Bond number is rho g LC square by gamma. Rho g LC square by gamma. So uh, we have, and then the capillary number is mu u by gamma. So we have capillary number times LC square by h square, scales as bond number. This implies LC square by LC by h whole square, scales as capillary power minus 1 bond number, which in turns is equals to LC by h, scales as capillary minus 1 by 2 bond 1/2. But we know, um, however, we know LC is equals to gamma by rho G. Basically, the balance of the gravity and surface tension. And at this region, we know that the bond number is equals to the characteristics length by capillary length. So therefore bond number at this region is 1. Substituting this, we get LC by H scales as capillary power 1/2. Therefore the correct option is here. So the correct option is A, as this implies H by LC will scale as capillary power 1/2. Therefore, option A is correct. Um, for the seventh question, we have which of the following statements are true for capillary rise in a tube? A. Surface tension force is the driving force. Both surface tension and viscous forces are the driving force. For obtuse angles, surface tension force is not the driving force. For obtuse angles, viscous force is the driving force. So if we look at the options, option B, both surface tension and viscous forces are the driving force. So when the meniscus is rising, uh, we have the surface tension force which points in the upward direction, and the viscous force acts in the direction opposite to the direction of velocity. And as the velocity is upwards, the viscous force is downwards. Therefore, the option B is untrue. For second case, obtuse angle. For an obtuse angle, we have here also the reduce in height is due to the again the surface tension force, and that is the driving force for the depression when there is an obtuse contact angle. And again, viscous force is opposite to the direction of the velocity. Again, here the velocity is downward, therefore the viscous is in the upward direction. This is the velocity, and this is the force viscous. So therefore, C and D are also wrong. So the only correct option is option A. So we'll read the question number 8. In a capillary tube of diameter A, 2 mm, the meniscus rise is given by the relation Z is equals to 6t plus 7 mm, where t is in seconds. Calculate the viscous stress tau mu considering a fully developed velocity profile, and the properties are given below. So we are given z is equals to 60 plus 7 mm, and the radius a is equals to 2 mm, which is equals to 0.002 meter, and we have theta e is equals to 0 degrees, rho is equals to 955 kg per meter cube, gamma is equals to 20 into 10 power minus 3 Newton per meter. We have viscosity is equals to 10 into 10 power minus 3 Pascal second, and G is equals to 9.81 meter square per second. So we are asked to find the viscous force, viscous stress, tau mu. So now we know for a capillary tube rise, Z dot is equals to U, and UR is given by 2Z dot by 1 minus R square by A square. So now we know the expression for viscous stress, which is equals to tau mu, which is equals to mu del U by del R at R equal to A. Moves with Z dot of T, and the viscous stresses at the walls will be given by mu del U by del R at R equal to A, which will be equal to the del U by del R will be given as 2Z dot. Z dot is just a function of time, so therefore Z dot comes out, and then minus 2R by A square at R equal to A. So we have minus mu 2Z. Yes, we have minus mu 2Z minus mu 4Z dot by A, and then there's mu. So it is minus 4 is mu Z dot by A. So that is the viscous stress. So if we substitute the values, we know Z dot, sorry, substituting the values, we know Z dot of T is equals to del by del d by dt of Z, which is equals to d by dt of um, 6t plus 7, and remember the units are in mm, so Z dot of T is equals to 6 mm per second. So substituting these values, which is equal to 6 into 10 power minus 3 meter. So tau mu is supposed to be minus 4 into 6 into 10 power minus 3 into mu, which is which is equal to 10, sorry, which is equals to 10 into 10 power minus 3 Pascal second, by A, which is 2 millimeter, which is equals to 2 into 10 power minus 3. So if we do the calculation, we'll get tau mu is equals to minus 0.24 Newton per meter square. So the correct option is 0. Minus 0. So from the problem given the previous question, we are asked what is the magnitude of viscous force F mu. So now we are asked F, find F mu. So now we need to calculate till what height has the fluid risen. So to calculate that, we need the height to which the fluid has risen, which is equals to h, which is equals to 2 into gamma into cos theta e by rho into g into a, which is equals to 2 into 0.072 into cos of 0 degrees by mm, sorry, we have rho as 955 into 9.81 into a. Okay, sorry, there's a correction here. We are given the diameter, so we have to be careful in taking the diameter. A is the diameter, so R is equals to 0.001. So here we will have, instead of 2 into 10 power minus 3, it should be 1 into 10 power minus 3. Similarly, here it should be the radius R should be equal to 10 power minus 3. So now we get the height to be 0.00426 h in meter. Okay, sorry. Height will be 0.02. Now we know the area at which the viscous forces have been acting. So F mu is equals to 2 pi r, which is the radius a, into h, which is a cylinder, into tau mu. So we already know tau mu from the earlier expression. So as we are asked to calculate only the magnitude, we don't include the sign. Then we have 2 into pi into 10 power minus 3 into 0.00426 into 0.24. So this comes out to be is equals to my the sign is negative, but the magnitude is 0.0064 millinewton, or 6.4 into 10 power minus 6 Newton. So this is the correct option. So we have, it is option B. So with this we end the week 6 discussion. Next week we will look at the week 7 solutions for the assignment of week 7. Um, so now I'll stop the recording here as there is internet issues, but I'll be on call to take up any doubts if anyone has any doubts. So the call is still running. I'll just stop the recording. Thank you. See you in class next week.